Okay, so let's talk about the integral test. So this is one of several tests that we're going to learn that can tell you whether a sequence converges or diverges. So here we go. If we have a continuous, positive, and decreasing function, and it only has to be these things on the interval from 1 to infinity. So it only has to be continuous, positive, decreasing on this interval. And we're going to talk about a series whose terms, a sub n, are given by this same formula, f of n. And right, here we go. So we are talking about this series whose terms are a sub n. And what this test does is it basically tells us that this series and this indefinite integral, where I integrate from 1 to infinity of this function f of x, they both do the same thing in the sense that either they both converge or they both diverge. So in practice, the way you use this is you're given a series and you're asked, does this series converge or diverge? And you just verify that the appropriate function is continuous, positive, and decreasing. And it has to be those things, or else you have to do something else. You can't use the integral test. But as long as it has these three properties, then what you do is you look at the improper integral and hope that this improper integral is something that you're able to do. And assuming you're able to figure out the answer to this, and when I say the answer, I mean whether it converges or diverges, that tells you the answer for the original series. So that does the same thing, whether it's converge or diverge. Okay. Also, if we're in the case where the series converges, which is the case where they both converge, so if that's the case, then we can estimate the error from partial sums using integrals. So what I mean is this is like, so this is the sum if I start at n equals k plus 1 and go to infinity. So in other words, this is like the leftovers. If I did this series and I added up a sub 1 plus a sub 2 all the way up to a sub k and I just stopped, this would be the leftovers. This sum would be the things that I left out, because this starts where I left off, because I'm saying that I stopped at a sub k. This starts at the very next one and goes to infinity. So, in other words, this right here is the error if I try to estimate the infinite series with a finite series, more specifically if I'm trying to estimate this infinite series and the estimate that I give is just adding up the first k terms, this is the amount of error in that estimate. And so what I'm saying is that amount of error is in between these two things, these two indefinite integrals. These are all, improper integrals. They are improper because they all have infinity in the limit of integration. Okay, so let's use this for something. So here's a question. You're going to be really familiar with the answer to this question by the end, but maybe we haven't seen this before. So does this series converge or diverge? And it's just 1 over n. Okay, what do? We talk about this function f of x, and f of x and a sub n are supposed to be, roughly speaking, the same thing, except if I'm using the letter x, I'll just replace the n with an x, so it's the same formula. So this is my function. I'm really only interested in this function from 1 to infinity. And by the way, of course, sometimes series don't start at n equals 1. They might start at n equals 2 or something, and then I would just do the interval from 2 to infinity. Like there's a version of the integral test that can start anywhere. But we're doing the standard integral test, so 1 to infinity. And we just have to check that it's continuous, positive, and decreasing. And so I'm just going to write these things down, and ultimately I'm just going to put check marks, but I'm going to actually check. It's important that we actually check these. We should not just be blindly putting check marks here. So we're supposed to check that f is continuous. Well, there's something that could actually worry me about this function, which is it's actually not continuous at x equals 0, but of course that's not in my interval. So I'm good. So we actually have to think about these things. In the end, it's all right, but we should think about these things. There's definitely going to be a time in your life where you want to use the integral test, but you find that it doesn't apply because it doesn't pass one of these checks. The next thing to check is that f is positive. Well, x could be a negative number, but not on the interval that we're interested in. So for the interval we're interested in, x is always a positive number, so 1 over x is also going to be a positive number. Okay, so we thought about it, and it's fine. And decreasing. It is going to be decreasing, basically because if I make the bottom of the fraction a larger number, that makes the fraction a smaller number. So that's some really basic logic. Sometimes it's not that easy to tell whether a function is decreasing, so let me describe another way. We already know the answer for this one, but let me describe another way. If you can take the derivative and find that the derivative is negative, that's a decreasing function. That's like Calc 1 stuff. As if the derivative is negative, then you're decreasing. So f prime of x, let's see. So this is x to the minus 1, so f prime would be negative 1 x to the minus 2. And we can see the negative sign right there. F prime is negative. So I ended up giving 2 reasons why it's decreasing, but we only need 1, so either way we're happy. Yeah. So this doesn't tell us the answer. This just tells us that the integral test applies. So to get the answer, meaning convergent or divergent, what I'm going to do is I'm going to look at the improper integral here, because whatever these two things do, it's the same thing. They both converge or both diverge. So whatever this integral does, the original series also does. Okay, here we go. So how do I do this? For an improper integral, I'm going to replace infinity with t and do the limit as t goes to infinity. This is an easy thing to integrate. So I'm there. T is going to positive infinity, so I can drop the absolute values. The absolute value, like if t is a large positive number because it's going to infinity, the absolute values aren't doing anything. Anyway, also natural log of 1 is 0, so nothing happens there. And now we get to our fun fact again. This has come up a few times recently. As t goes to infinity, natural log t goes to infinity. So, in a sense, we just got an answer, but in terms of questions of convergence or divergence, if the answer is infinity, we say it diverges. We're not saying that it converges to infinity. That's kind of nonsense. We say it diverges. And maybe this is the first time I've done this, but when I answer these questions, I try to be very specific. Like, we're talking about two different things. We're talking about the series and the integral. And so I'm going to be careful when I say stuff like it diverges or it converges. What is it? You know, that has to be clear. The integral diverges. So the original series also diverges. So see, I'm being careful to, instead of saying it diverges, I'm saying the original series. So somebody reading it would understand that I'm referring to this, that this was what the question was about. So anyway, we got our answer. The original series diverges. Okay, so that was part of a more general fact that I'll now tell you. So a p-series is a series of the form 1 over n to the p. So we just did 1 over n, so that was like p equals 1. And I'll just go ahead and tell you the answer for p-series. You can find this using the integral test, like we just did for p equals 1. You can do the integral test for any value of p. This converges if p is greater than 1, and it diverges if p is less than or equal to 1. And just to remind you, we just did the case where p is equal to 1, and we found that it diverged. So it goes with what I'm saying now. This is worth remembering. P-series come up all the time. Okay, so let's do another example. So now that we know all about p-series, we know that this converges, right? Because this is like the p-series where p is 2 and 2 is greater than 1. So this definitely converges. What we're going to do is we're going to estimate the value with an error of at most 0.1. So this is where this statement comes into play. This is a statement that allows us to estimate sums. So if my estimate is going to be the sum from 1 to k, then the error, maybe I should put this on the screen. So this is the amount of error from estimating an infinite sum that starts at 1 and goes to infinity with a partial sum which stops at n equals k. That's the amount of error. And what this is telling me is, on the upper end, this is telling me that the error is at most this. So my function f is 1 over x squared because my series is 1 over n squared. And so I just wrote this down. Okay. So let's do this. This is the limit as t goes to infinity because I have an improper integral, of course. It's like this. This antiderivative is -1 next to the -1. So I'm like that. So this is negative t to the -1, and then I would subtract, so it's going to be plus k to the -1. So yeah, this, of course, t to the -1 as t goes to infinity, that's like, so this is like 1 over t, so this part goes to 0. So in the end, I just get k to the -1, or 1 over k. So what does that tell me? We just said that if my estimate is going to be adding up the first k of these numbers, then how far off am I going to be? I'm going to be off by at most this much. Now, I want my error to be at most 0.1. So I want this error to be at most, here I'll write 1/10. So what value of k do I need to pick to make that true? And keep in mind, it's going to be less work for me if I choose a smaller value of k. So the smallest value of k I can pick to make this true is 10. I could pick anything at least 10, but that just means that I would have to add up more terms, because remember, I'm going to sum this from n equals 1 to k, so if I choose a large value of k, that's just more work for me. You get a more accurate sum, but I just want my error to be at most this. So as long as my error is at most this, then I'm happy. So I'm going to add as few terms as I can and still guarantee that my error is small. So my estimate is going to be adding up the first 10 of these numbers. So that's 1 plus a fourth plus a ninth, all the way up to when n is 10. Oops, that's too many zeros. All the way up to 1 over 100. And for this, I would recommend a computer or calculator or something. It's a bit, you don't want to really do this by hand. This is about 1.5, and I rounded off to 1 decimal because we only know that this is accurate to within 0.1. In fact, if I do the infinite series, it's about 1.6, so indeed we are off by about 0.1. But anyway. So that's how to use the integral test to estimate a series.